Yeah, maybe because I didn't advertise it 1 week in advance as usual. There's less people, but there's many people that watch it afterwards, always on YouTube. All right. Okay, so we're ready to start.
Okay, I'll share my screen then. Oh, I can't share my screen. You may need to give me more permission.
Okay.
Okay, great. Do you want me to start any time or?
All right. So we have today, I make a short intro, very short. We have today Richard Howl and Devang Naik that will give us a talk on testing quantum gravity with non-Gaussianity and the Bose-Einstein condensate. This is a paper that was a collaboration of several people. Richard is the first author, and Devang. There's Vlatko, there's myself, there is Carlo Rovelli, and Aditya Itier, right? So Richard, if I understand well, will talk more about the theoretical part, and Devang, who's an experimentalist in Bose-Einstein condensates, will give afterwards a bit more details on the experiment. Whenever you're ready, Richard.
Okay, yeah. Hi, everyone. Yes, so first, yeah, thank you very much to Marius and the organizers for the invitation to present our work. Yeah, you know, I really enjoy these KISS seminars, watch every 3 weeks, and I think the format is fantastic. So yeah, it's great to be actually presenting one. Yeah, so this test is based on a proposal for testing quantum gravity in the lab that was published last year with Devang and, as Marius said, quite a few KISS colleagues. And yeah, I'll provide the motivation and more theoretical aspects of the work. And then I'll pass you on to Devang, who will provide experimental expertise on what is actually needed to make this sort of test a reality. Okay, so first, let me be honest. I actually have a particle physics background from my sins. And when discussing how to see quantum gravity effects in experiments, we always spoke of how you'd likely have to probe the Planck length scale, which is unimaginably small at 10 to the minus 35 meters. So this is where the Schwarzschild radius of a black hole is comparable to its reduced quantum wavelength. So a place where GR truly meets the microscopic world of quantum theory. And all sorts of things might happen here, such as vacuum fluctuations of space-time curvature, completely distorting measurements of distances, or it could be the length of strings in string theory, for example. So to probe this scale in the lab, the idea is that we'd have to use a particle accelerator, as these are essentially the best microscopes you can build. But this would mean smashing together subatomic particles with Planck energies, which seems hopelessly beyond our capabilities, with talk of needing accelerators the size of the solar system or even the Milky Way. If it could be done, though, getting to the Planck length scale would in principle allow us to distinguish between different theories of quantum gravity. But that presupposes that gravity must be quantized, which is what the vast majority believe, and for very good reasons. But there is no actual direct experimental evidence for this, so we cannot say for certain if this is really the approach nature takes, if we really have a quantum theory of gravity. Indeed, in the early days of trying to unify GR with quantum theory, there was a bit of debate about whether gravity should actually be left fundamentally classical, as it seems so much harder to quantize than the other interactions. And, of course, it's also theoretically quite distinct with background independence, for example. So several theories have been proposed that keep gravity fundamentally classical, but still quantize matter. So an example is semi-classical gravity, where the fundamental classical gravitational field is sourced by the quantum expectation value of the energy of quantum matter. So there is but there's a bit of debate about whether these theories are played with theoretical issues such as superluminal signaling at certain scales, but we cannot discount them until there's experimental evidence. And indeed, if we were able to discount them, then on the flip side, this would actually provide the first experimental evidence that gravity must obey quantum theory, which I think is very exciting. So this subject was much discussed at a Chapel Hill conference in the 1950s, where Feynman introduced an idea of how you could test if gravity is fundamentally quantum or classical in the lab. So from the proceedings of this conference, it's not 100% clear what this experiment was, but my take on it is that there's a Stern-Gerlach device, which is used to place a macroscopic mass in the superposition of two locations. So that's the little circles on the left. And then another mass, the circle on the right, that is not initially in a superposition, it is placed near that left mass. Then if gravity is quantized and quantum theory is universal, the mass in a superposition will create a gravitational field or force in the superposition. And this would then cause the mass on the right to be in a superposition branch of going one way or the other. Yes, although Feynman never explicitly states it, but the full system would, of course, be entangled. Although he does mention using reverse Stern-Gerlach devices for measurements, so I don't know, maybe he really did have this in mind. But yeah, so quantum gravity leads to entanglements, but if gravity was classical, then there can be no superposition of fields, and the second mass would therefore not be part of an entangled state. So the experiment seems to provide a way to tell if gravity obeys classical or quantum theory. So before we spoke about the Planck length as the place we need to probe to see quantum gravity effects, but this sort of test seems to be better characterized by the Planck mass, which appears far more within reach, well, for composite mass at least. And yeah, this was nicely demonstrated by Maris and Carlo in the context of more recent proposals, and also happens to be connected to some old arguments of Penrose that this is another place where the unification of gravity and quantum theory becomes important. So I like to think that with our particle accelerator experiments, we're in some sense bringing gravity, bringing space-time curvature to the traditional microscopic scales of quantum theory, whereas here we're sort of doing the opposites. We're bringing quantum theory, bringing quantum coherence to the traditional scale of gravity with large masses. Now, until relatively recently, that proposal of Feynman's had been forgotten about, perhaps because technology was going in the direction of particle accelerators and probing smaller length scales. But as progress in that area has slowed down, rapid developments have been made in taking quantum theory to larger scales, which has brought this proposal back to attention again. In particular, there's been a lot of interest in the idea that entanglement could be used to verify the quantum nature of gravity. And this has culminated in a fairly general argument that if you have two isolated matter systems, say A and B, and they only interact through the gravitational field, say C, and not directly with themselves, then if gravity is classical, there is no way it can entangle with a quantum mass by definition. And so there is no way the two masses can become entangled with each other. Whereas if the gravitational field is quantum, then it can entangle with the masses and so cause the two masses to become entangled. So the summary is that if gravity acts locally, verification of entanglement between two masses would provide evidence of gravity being quantum. So then, using this argument, two quite remarkable papers appeared showing how such a test of quantum gravity may really not be that far away. So these proposals boost the feasibility of Feynman's by also placing the probe mass, the mass on the right, in a superposition of two locations, and looking at the entanglements due to how gravity creates a relative phase shift in the superposition of the masses, rather than in how they move. So the phase difference that results in entanglements can be well approximated by just working in the Newtonian regime of gravity, and can be written in terms of Planck units, the time of the experiment, and the distance between the masses. So that's the lower red box. And then maximum entanglement is obtained when this phase difference is of order 1, which can be achieved with various experimental parameters. And yeah, I'll talk about the feasibility of those on the next slide. So these papers made a big impact, which of course will always lead to much discussion and also many questions. And I'm not going to go through all of these questions, but I'm going to talk about just one or two because it'll be useful for the rest of the talk. So one of these is to do with locality. So locality can mean different things in different communities. And here locality means that the two masses must not directly interact with each other. So the interaction must be local to each mass, which if violated may not necessarily imply superluminal signaling, for example. Now, locality is, of course, an important tenet of modern physics, and we have evidence that this is the way nature behaves. So in my opinion, it'd be rather peculiar if the way GR and quantum theory connect is non-locally, at least at the scales of interest. So if the locality assumption seems pretty reasonable, what has the discussion been about? So there seems to be several discussion points. One being that, although perhaps it's not quite the same, non-locality can crop up when unifying quantum theory and GR in quantum gravity theories, such as in string theory, which may be approximated by non-local quantum field theory at lower energies. And non-locality has also been suggested in theories with classical gravity, for example, as a way to explain dark matter and dark energy effects. And there are even some discussions, perhaps more importantly, that if you want gravity to be fundamentally classical, then you're going to be led to a non-local theory in general because of how classical gravity is sourced by quantum matter, with even some suggestions that semi-classical gravity, the sort of archetypal theory of classical gravity, could potentially be non-local due to its non-linearity and non-unitary dynamics, and thus possibly it could even create entanglement in the experiment if the theory is treated absolutely rigorously. Now, I think there's much to be understood here still, but I don't want to go into the details. I really just want to highlight that there has been a fair amount of discussion on the generality of this entanglement argument, given the locality assumption. And also that this assumption has seemingly led to other confusions, such as the fact that the entanglement papers use Newtonian gravity, which is non-local, of course. And so you could be led into thinking that this would imply that you will always have entanglements, whether gravity is classical or quantum, since gravity is non-local in this regime. But this is, of course, not true in reality because Newtonian gravity is just used as an approximation to relativistic gravity in these papers, nothing more. And a bit of an advert, we rigorously go through this in a very recent paper where we show that according to relativistic quantum gravity, entanglement only occurs after the light crossing time between the two masses. There are also, of course, questions over the true feasibility of the experiment, with spatial superposition states needing to increase in mass by 9 orders of magnitude compared to what we can do in the lab at the moment. And still for these to have long coherence times and large separations. So there's no getting away that this really would be a big jump, but this field does seem to be making rapid progress. So there is also thankfully a lot of hope. But at the same time, it is unclear how far away this experiment actually is. And there are also some other questions that I believe are mostly based on misunderstandings, which I'm not going to go into here. Okay, so I can probably tell that I'm not especially worried by a lot of these questions, except for perhaps the one on feasibility. But we still decided to explore whether entanglement and these micro-object experiments have to be the way to go, or if there is an alternative approach to testing if gravity is quantum that could help answer some of these questions that are causing much discussion. So the entanglement argument has been looked at a lot, and not just from a quantum theory perspective using LOCC, but also trying to be more theory independent using generalized probability theory and constructor theory, for example, and so not relying on specific dynamical laws. Whereas as a first attempt at looking for alternatives, we strictly followed a dynamical law approach, so leaving theory independence for another time. So yeah, I'm going to introduce this alternative approach using the weak field limit of gravity, since this is a well understood description of gravity and is very much expected to be valid at the experimental regimes of interest, which is what's important, of course. So here you split the metric into a background and a perturbation, and then gravity and matter couple through an interaction Hamiltonian density via the stress energy tensor of matter. Then, as with the entanglement argument, we will assume that all of the interactions can be neglected. So with matter obeying field theory, the stress energy tensor only contains kinetic terms that are necessarily quadratic in the fields. And here I'm using a real scalar field phi to represent matter, but this is just for simplicity. The argument holds for all types of fields, scalars, spin a half, etc. So then we assume that at least at the scales of interest in the experiments, matter obeys quantum field theory. So we add a hat to this phi field. Then if we have quantum gravity, we assume that there must also be some quantum operator associated with at least some of the components of the perturbed metric. So we add a hat to H. Whereas in contrast, if we have a classical theory of gravity, then we assume that although matter is quantized, there is no quantum operator associated with the gravitational field. It is fundamentally classical, so we leave the metric hatless in that case. So then the two types of theories are assumed to have Hamiltonian interaction density terms given in this blue box here. And we noticed that the classical gravity one contains just two field quantum operators, which means it will necessarily preserve Gaussianity of matter, which I'll come on to more on the next slide. Whereas for quantum gravity, there are free field quantum operators, which means that it can, in principle, generate non-Gaussianity in the quantum field state of matter. So that basically means that we could turn a Gaussian matter state into a non-Gaussian matter state only with quantum gravity. So detecting that Gaussianity of a quantum state of matter has not been preserved could be used as evidence that gravity is quantum. Okay, so now, let me go through that in a little bit more detail. So Gaussianity and non-Gaussianity, I think, are well understood in quantum field theory, where you have Fick's theorem, also in cosmology, where you have Gaussianity and non-Gaussianity of temperature fluctuations of the C and B. And it also happens to be studied a lot in quantum information theory, which I'll come on to in a little while. And one way to characterize Gaussianity, which is perhaps most used in quantum information, is to first expand the quantum fields in annihilation and creation operators. And yeah, again, I've just used a discrete mode spectrum just for convenience. And then we can write these like the position and momentum operators x and p of a simple harmonic oscillator. So then a pure Gaussian state is one that is fully defined by the first and second order moments of these operators, just as a Gaussian function is fully defined by its first and second moments. But there's other ways to define it, other equivalent ways, such as through field expectation values and field correlation functions. And a Hamiltonian that is just quadratic in these x and p operators, without couplings to any other operators, has been proven to always preserve Gaussianity. So a Gaussian state will always remain Gaussian. And yeah, as we argued on the previous slide, this is what we have with classical gravity, as there were just two matter field operators, and the gravitational field is then absorbed into the coupling terms of the Hamiltonian. And yeah, as ever, there are equivalent ways to show this, such as using the path integral formalism of quantum field theory, where you have Gaussian integrals. On the other hand, a Hamiltonian that is not of this quadratic form can induce non-Gaussianity, which is the case for quantum gravity. So just if, in case there's people that are not familiar with Gaussian and non-Gaussian states, some examples of Gaussian states are the vacuum and coherent states, squeeze vacuum and thermal states. And these are characterized in the bosonic case by a Gaussian Wigner function, which are shown here and are always positive. Non-Gaussian states, on the other hand, include Fock states and cat states and have Wigner functions that are non-Gaussian and can be negative. And interestingly, an entangled state can be Gaussian or non-Gaussian, and a separable state can be Gaussian or non-Gaussian. So there is not a strong correlation between these different types of states in this regard. And also, while entanglement requires two systems, of course, a single system can be Gaussian or non-Gaussian. So just quickly, the reason non-Gaussianity is much studied in quantum information theory is that it's needed for universal quantum computation. So you can't just do that with Gaussian states and operations. So I think this really illustrates the quantumness of these states and operations. Okay, so now I've introduced it. Is there any point in using this alternative approach rather than looking for entanglements? Are there any advantages? Well, to help answer this question, I thought I'd first reiterate what I think are the key assumptions behind the idea. So these are that matter obeys quantum field theory in the regimes of the experiments, and this is accessible to the experiment. And as with the entanglement arguments, we also assume that all of interactions can be neglected in the experiment. So unlike with the entanglement arguments, noticeably, we didn't specify a locality assumption, which is why I spoke about it earlier. So, there's no obvious LHC here. And so it's possible, therefore, that non-Gaussianity does not rely on locality, and this could rule out both local and non-local theories of classical gravity. So a further hint that this might be the case is provided by working with a non-local quantum field theory, where you drop the locality assumption that is, of course, usually made a requirement of quantum field theory. So these non-local theories, they've been studied a fair amount in the literature, particularly in the context of string theory, and they tend to come with potential issues such as with causality. But I'm just going to ignore these issues just to illustrate the point. Okay. So in this case, if we wanted a non-local matter-gravity interaction, and if we really wanted such a thing, then we would make sure that the interaction then doesn't have to take place at a single space-time point, which is what's going on at the top of the slides. But making the coupling non-local in this way does not affect the fact that classical gravity preserves Gaussianity, since we still have just two quantum matter operators, and so it preserves Gaussianity. Whereas in contrast, in this non-local quantum field theory, you can get entanglements between two space-like separated masses now, so entanglement from a non-local classical interaction, which of course, we already knew. So I really don't want to give the impression that I'm in favor of these non-local theories, but I just want to illustrate that non-Gaussianity may potentially present a way to just avoid any discussion or confusion on locality that seems to occur when you talk about entanglement. And then also related to this is that we only need single systems to detect non-Gaussianity rather than two systems, which has the advantage of possibly simplifying experimental setups, which I'll come on to very soon. So those are some potential advantages. But to be fair, I think the approach may also come with some disadvantages. So for example, at the moment, as I've said, there's no theory independence approach, whereas this has been looked at to some degree for the entanglement arguments. So yeah, it's lacking a more general approach. But one speculative idea we've had on this is to look at quantum contextuality, since non-Gaussianity is connected to negative Wigner functions, which are connected to contextuality. And very speculatively, this might also explain why locality could not be a requirement, as contextuality can in some sense be seen as more general than Bell's theorem, with that essentially deriving from contextuality over space-like regions. So yeah, as I say, this is speculative, although one thing we have shown that is related to this is that the creation of non-Gaussianity in the most general sense seems to really require non-commutativity of gravitational operators, which from LOCC is also a requirement of entanglement generation. And we've also looked at a few cases beyond quantum theory, such as non-Hermitian gravity, and where gravity acts as objective weak measurements. But as I say, a more general framework is needed. There are also, I think, some other disadvantages, such as it not being as intuitive, which I don't think I have time to go into now, but would be more than happy to discuss after the slides. Okay, so now I'll describe a possible tabletop test that uses this alternative approach. So this test is based on a single atomic BC, where, of course, identical atoms macroscopically occupy the ground state. And these were first demonstrated in '95 and have since been developed in many, many research centers around the world. So Bose gases are many body systems, and the way we describe them is to use a non-relativistic quantum field, where psi dagger here would create an atom at position R. And then in the approximation that only the ground state is occupied, we can just use a single mode of this field to describe the system, where then we have a single annihilation operator, which of course destroys atoms in the ground state. Okay, so then when you look at how the BEC self-interacts through gravity, it's appropriate to consider gravity in just the Newtonian regime, since the BEC is effectively non-relativistic. And then you find that the quantum gravity interaction Hamiltonian is quartic in the ground state operators. So it will induce non-Gaussianity in the BEC, whereas the classical gravity one is quadratic. So it will preserve Gaussianity, which of course follows from the more general argument. This is just the mathematics for the BEC. So it turns out that the BEC is naturally in a Gaussian state, leads to a good approximation. So any sign of non-Gaussianity that is developed in the BEC could be used as evidence of quantum gravity self-interactions. And it's possible to develop a signal-to-noise ratio, an SNR, for a measurement of non-Gaussianity of the BEC, which really you want to at least be above 1, you want the signal to be greater than noise for the experiment to be feasible. And it turns out that for a squeezed spherical BEC, this ratio takes the same expression as the phase in the entanglement experiments, which characterizes the feasibility of those. So we just replace the distance between the microspheres in that case, the big D, with the radius of the BEC, which is R. And we also introduce curly M, which is the number of repetitions of the experiment. So then if you want a similar signal to the entanglement experiments, this would mean generating a BEC of around 10 to the 9 atoms, which is quite high for BECs. But as Devang would explain, this has to some extent been achieved in the lab, but there is still more work to be done. And as well as high atom numbers, we also need to squeeze the BEC, and we need to maintain it for a second or so, which will be very challenging. But on the plus side, cold atoms with quantum squeeze states have at least already been produced in the lab. So in summary, we have a tabletop test of quantum gravity that is based in principle on a single quantum system, doesn't rely on local interactions, has no challenging spatial superposition states, which are often called noon states. It should have good repeatability, as with other BEC tests. And there is already some technology for the type of initial states needed and the type of measurements needed. But in any case, I'll now pass you on to Devang, who will provide far more detail on the experimental requirements and what actual hope there is for this sort of test. All right.
Thank you very much, Richard. Maybe we can make a pause here before Devang
Sure.
part in case people have questions for this first part. Ali, yes.
Thank you, Marius. So thank you, Richard, for the very nice talk. It's always nice to watch your talks. Always clear and interesting. So as I understand, you distinguish two cases. In the first one, only the matter is quantum, so there are two operators or two powers of whatever operators in the interaction Hamiltonian. And in the second case, the matter and the fields are quantum in a sense.
Yep.
So you have 4 powers of the operators, right?
Yes. So yeah, if we can go back to it. So yes, in the more sort of general setting of weak field gravity, yes, you have always we assume matter is quantized, and then but only in quantum gravity do we assume that it's also the gravitational field. Yeah.
Okay. So this is one sense in which we can say gravity is quantum. However, is this what everybody means when they say gravity is quantum? For example, if I do this experiment and I see the non-Gaussianity, I see the Wigner, the state evolves, the Gaussian state evolving into a non-Gaussian state. Does it, for example, imply that I will see the graviton? I mean, does it imply that the graviton exists?
I think in some sense, yes. So if I if I go to some other slides, so my argument on that would be to consider some Feynman diagrams, and in the quantum gravity case, yeah, you have like you can have obviously the emission of a graviton, and this process obviously would have a vertex that's associated with 3 quantum operators, and that's why you're getting non-Gaussianity. Whereas in the classical gravity one, you obviously don't have a graviton. You have gravitation, a classical gravitational field, and so you sort of put a cross at the end of the propagator to say you can't make this virtual anymore. And in that case, of course, you only have 2 quantum operators at the vertex. So in some sense, I'd say that the existence of a graviton tells you that you would have non-Gaussianity, but yeah, seeing non-Gaussianity would not necessarily imply that there must be a graviton. Similar to like the entanglement experiments, how if you see entanglement, this may not necessarily imply, completely that there's a graviton, because the effects can be explained by taking the Newtonian regime of gravity. So it's exactly the same here. Non-Gaussianity in these tests could be explained by working in the Newtonian regime of gravity. So you could have some people might say, yes, that this is not really a test of quantum gravity because we're not seeing a graviton in the experiment. Does that answer your question?
Yes, thank you.
Yeah, cool, thanks.
That's another hand if we can be quick though, so that we can have a discussion session at the end. Kim.
Hello, thank you. My question is somewhat relevant, somewhat related, I guess. So when you, let's say you make the experiment and you see that it's non-Gaussian, or what are the other factors that would give the same result, and how do you know how strong they would be in comparison to this effect? Because I would imagine there would be any number of like both experimental and factors, and also factors that are relevant to other interactions that you cannot really screen against. So
yeah, I mean, Devang will talk about this more. So maybe I can just be very quick perhaps and just say, yeah, there obviously will be other interactions, like all quantum interactions will create non-Gaussianity. That's our argument. So electromagnetic interactions in the BC would also create non-Gaussianity. So you find a way to suppress these or distinguish them from gravity. And we do this using Fetchbox resonances. But maybe this is best for Devang to give his talk, and then because he can properly explain what's going on there, rather than me just repeating what he's going to say.
All right, I think this is a perfect pass for Devang. I actually have the same question, although I'm co-author. How convinced are we that we can screen the other interactions?
Okay, perfect. Let me just share my screen.
Yeah, sure. I'll stop sharing mine perhaps.
Would it be okay if I just ask one more very quick question? I promise you it's very basic.
Oh, yeah.
I just wanted to ask, for someone who's never met BECs before, there was I guess it was on the previous slide, Joe, now, but there was a creation operator defined at one point where, the interaction ends up being quartic in the creation operator. I just wanted to know what the sort of physical interpretation of that is. Obviously in QFT, you create particles, but I'm not really familiar with what BECs are. So what is that A dagger like actually creating?
Yeah, with the
yeah. You want your screen, Richard?
Oh no, it's fine. Yeah, so I mean the A dagger would be just creating like a momentum state in the condensate. So it wouldn't be a momentum state. It'd just be creating an atom in the condensate, essentially. So you'd have the full operator of the fields at evaluated at some position R with a dagger. That would be creating an atom at position R, but it could be any mode, of course. And then this A dagger here is just meant to be creating an atom in the ground state, in the condensate.
Jakob, maybe I could add something else. So experimentally, there's no really such thing as 100% condensate. A condensate always exists in equilibrium with the thermal cloud right above it, and the atoms are constantly being shared between them. In fact, the BEC is a state with the maximum number of fluctuations in atom numbers. So you have atoms from the BEC constantly going to the thermal cloud, and atoms in the thermal cloud constantly going to the BEC. So this is what the A daggers stand for.
Okay, thank you.
Does that make sense?
Yeah, I think so. Thanks.
It's actually really strange because I see a lot of theory papers where they really almost talk about, assume 100% BEC. But if you have all your atoms in a BEC, you don't really have a BEC because you have a fixed number of atoms. So
yes, it's a simplification that,
yeah.
But it happens to be one that works fairly well.
Okay.
I think from a theorist point of view, maybe not from experiments, I don't know. But
well, we do something even worse. We just ignore the thermal cloud and just pray it doesn't cause any problems. So my name is Devang. First of all, thank you, Marius, for letting me speak, and thank all of you for being here. It's nice to be around theorists because I'm really just surrounded by experimentalists most of the time. I want to do a really quick recap of all where we are in ultra-cold atom technology, specifically technology that's more germane to test of quantum gravity. I'll go fast through this, but you could ask any questions you want afterwards. And most of the work I'm going to talk about is work I personally am involved in, but whenever there's a better type of work that's more interesting, I'll mention this. I always like to show this graph because to show where we are in terms of technology. This is more or less a logarithmic graph of temperature. And you can see on the top, you see the temperature of liquid nitrogen and the temperature of freezing water. It's a very small part of this curve over here. On the upper part, you see the surface of the sun, which is a few thousand Kelvin. So our normal experience is really in this small part on the top right over here. However, in the last few decades, ultra-cold atom technology has really progressed to where we could cool 9 to 10 orders of magnitude below ambient temperature and arrive at quantum degeneracy at nanokelvin temperatures. There are some groups that even mention picokelvin temperatures, but at the temperatures we're at, the use of temperature is really not even a good parameter. It really doesn't make sense with the levels we're at right now. Now, okay, perfect. The two technologies that really helped getting us there are optical cooling, which is the standard magnetic optical trap, and Sisyphus cooling, which brings us from ambient temperature to microkelvin. Now, at this point, just rescattered light limits the temperature. So we have to use another technique, which is generally evaporative cooling. And this is in principle nature's most effective cooling mechanism. However, it revolves around ejecting hot atoms and letting the colder atoms rethermalize, which means you're constantly losing atoms. And this could be a serious limit in terms of the total number of atoms you could have in the quantum states that you're trying to engineer. Now, the combination of these two techniques have allowed us to cool and trap atoms to quantum degeneracy all over the periodic table. And every one of these atoms have really interesting physics. But I want to focus on 3 atoms, which is most germane to what we're talking about here. So usually when people talk about BECs, they always mention these large numbers, 10 to the 9 atoms and 10 to the 10 atoms of BECs that are created. And this is possible for one and only one particular atom, the hydrogen atom. And the reason for this is the hydrogen atom has 3-body collisions which are extremely low. So evaporative cooling really depends on collisions, and 3-body collisions is a loss mechanism. And this has the largest amount of 3-body collisions. So we can perform really good quality evaporative cooling to arrive at these huge atom numbers. And also hydrogen rarely forms molecules. So you can use other molecules as coolants, atoms as coolant to really drive the cooling process even further. The only issue is hydrogen A is low mass. So even you could have 10 to the 9, 10 to the 10 atoms, because they're low mass, you don't really have the largest amount of mass in your quantum states compared to other atoms. The other issue is related to what Jakob actually asked. So in hydrogen, the BEC fraction is very small. So even though we have a large amount of atoms in hydrogen, we have even more atoms that exist in a thermal cloud, which is constantly colliding and exchanging information with your quantum state. And that is a potential decoherence channel. So it's really not the best sort of thing for these sorts of experiments. And also, as I'll mention a bit, we use optical transitions to be able to image and manipulate these atoms. And hydrogen has optical transitions, strong ones in the extreme UV. And there's not many good quality lasers that exist for that. Instead, the second best atom is sodium. This used to be the workhorse for all ultra-cold atom experiments. It has collision rates between 2-body and 3-body, which are almost ideal for evaporation, second only to hydrogen. Also, its optical structure is perfect for laser trapping and cooling, allowing us to get really large BECs, about 10 to the 8. I can show you a little. This was actually my experiment in the US. At that time, we created the largest atom number BEC, close to 100 million. We've now been beaten by a group in Utrecht. But now we could get to about 500 million atom BECs. And more importantly, we could get to them at really good condensate fractions. So at these temperatures, we don't talk about temperature anymore, even though we're in the tens of nanokelvin. We talk about enthalpy per particle. And sodium has the smallest enthalpy per particle, creating a very nice system. In fact, the combination of the enthalpy per particle and the large atom number allows us to do many interesting things. We could create large vortex lattices. We could even create BECs in really strange spatial geometries. On the bottom right is our BEC in a ring geometry. Also, it looks cool. So sodium has a yellow light. So the lab of sodium, you can see yellow, green, various really nice looking colors. However, sodium has an issue, and this is related to another question that was asked about other forms of decoherence. So ultra-cold atoms are very isolated. You could isolate from the environment, everything in high vacuum systems. However, there are 2 electromagnetic interactions which can be really a problem, and that's 2-body and 3-body interactions. Now, fortunately, ultra-cold atoms has a very nice thing called Fetchbox tuning, which allows us to control these 2-body interactions. Sodium has this property too, but it's more difficult. The best atom for this is one right below it in the periodic table, potassium. Although large atom numbers of potassium have yet to be realized, in principle, it can be realized because potassium has good collisional properties with sodium. So you can use a bath of sodium to cool down the potassium. However, I want to talk about the first major advantage of this, and this is Fetchbox tuning. This might be too simple for many people, but I'll just go through it just in case no one knows it. So at the temperatures we're dealing with, there's only one type of collisions that occur, and that's S-wave symmetric collisions. In principle, you could have 2 atoms that have a collisional potential energy shown as this. When they're far away, there's very little interaction, 2-body interactions. When they come closer together, there's an attractive region. And when they're too close, there's a strong repulsive region, which is like a hardcore repulsion. In that attractive region, you can have molecular states that are formed. And I want to ignore most of these molecular states except for the very top molecular state. Turns out we could define the entire S-body scattering and the scattering rate via just the energy of this top scattering rate. And this is something nature gives an atom. It's not something you could really control. However, these are alkali atoms, and the alkali atoms have electrons, valence electrons, which have spins. When these atoms come together and start to collide, the spins of these electrons matter and change this potential. The spins can be a singlet state, in which case we get the potential we have here, or it could be a triplet state, in which case we get another potential that's slightly shifted in energy simply because the spin is different and the magnetic field will create the energy difference. With that same magnetic field, we could actually tune this energy difference, and we could go to a point where a bound molecular state of the triplet atom configuration is exactly on resonance with the free energy of the singlet atom configuration. Now, the collisional energy of these two free atoms is no longer given by its own scattering potential, but it's given by this other scattering potential, which is brought on resonance. This creates really interesting phenomena. So when it's right on resonance, the Fetchbox resonance, at this magnetic field, as you can see on the bottom right, the scattering length can blow up to plus or minus infinity. Of course, experimentally, it's limited by other factors. Yes, Jakob? Do we have a question? Sorry.
I think the hand stayed up from earlier.
Okay, sorry. Okay, no worries. Okay, well, we could tune the scattering length to really large values, and we could even take it to 0. This region is called the Fetchbox resonance, and this region allows two really interesting things. First of all, it allows us to go close to 0 two-body interactions. Now, it's close to 0 because there's second and higher order things that occur when the two-body interaction is 0. However, using tricks, we could even cancel them out in one direction. So we could really zero out two-body interactions with this method. And more importantly, we go to these high scattering lengths, minus 10,000 to plus 10,000 A0, which is known as the universal regime. This is a regime where the scattering length is so large that it overpowers anything else in the system, such as temperature, density, trap inhomogeneity. This creates a very simplified sort of system to where you could describe your dynamics. Now, not only two-body, but actually three-body, we have good control over. So one of the things that we do in our lab is continuously we load atoms inside optical lattices, which reduce the dimensionality of the system. We could put it in three-dimensional, two-dimensional lattices, or even in one-dimensional tubes. The graph you see on the bottom right is what happens when we increase the strength of these lattices. And reducing the dimensions, the dimensionality, especially in one dimension, going to one dimension, allows us to reduce three-body interactions by 4 orders of magnitude. So this is one of the strong advantages. We have really close to full control over these electromagnetic forces, which can cause other sorts of decoherence channels. Now, okay, this is what a standard sort of ultra-cold atom laboratory looks like. This is a lab that I particularly built, and this was in Innsbruck, not far away from where most of you are. This is a standard laboratory. It has an oven, a Zeeman slower. In the center, it has an ultra-high vacuum system. We create vacuums that are better than 10 to the minus 11 millibar. And we see a zoom of this. On the bottom is a glass chamber where all the experiments occur. And you can see two blobs, a red and a blue. So this system was a particular system where we could cool and trap 3 atomic species, lithium, potassium, and strontium, and all their isotopes. What you see here is lithium and potassium. Strontium is also there, but you can't see it by the eye, so it's invisible. And one of the things about the modern day laboratories is they're very reproducible, repeatable. We could actually create an experiment, this particular experiment, for example, we were able to do these long runs where we could have the lab running 24 hours a day, 7 days a week for months on end. What the data you see here is just Fetchbox spectroscopy, identifying Fetchbox resonances, which is a very labor-intensive process. We were able to do this in the span of 6 months, and we rarely ever actually enter the lab. It was all controlled via computers. And more importantly, we could create protocols to create states. In particular, what we're talking about here is squeeze states. But any sort of complex quantum engineered states, we could create them in deterministic fashion. So every time we run the experiment, we could always start from the same conditions with the same amount of whatever, whether it's squeezing, whether it's formation of molecules, or whether it's strongly correlated systems. This is a huge advantage that we have that other platforms don't have. We can also combine the two types of control. This is actually a lab that we built in Florence, Italy. We were able to control both two-body and three-body interactions via both Fetchbox resonance and optical lattices. So we took condensates of about 1 million atoms and we loaded them into one-dimensional tubes where we could reduce the three-body interaction by 4 orders of magnitude. And then we could actually just control the two-body interactions, going from 0 all the way to 10,000 A naught. So it gives a lot of flexibility in this case. The only issue we're dealing with here is when you want this full control, you're dealing with atoms in one dimension. So we're dealing with one-dimensional systems, and this might change toward the dynamics of everything. But just as important as creating all these systems, we have to properly image them. One of the big problems with ultra-cold atoms is how do you image them, especially if you create a really interesting quantum state. Well, we developed several techniques that are actually germane to this discussion. One of the things we talk about in the paper is how to use higher correlations of the atoms in the squeeze state to test for non-Gaussianity. We actually have really nice techniques to measure these higher order correlations, which I want to describe a little bit here. So usually if you have ultra-cold atoms, we usually just take a picture, and the picture looks like what you see on the left-hand side. These are actually ultra-cold atoms loaded inside an optical lattice and created as crystalline structure. However, if you take an image, you just can't see any information about the crystalline structure. If you take a slice from this image and plot it, you see a lot of noise along this slice. Turns out that this noise has valuable information, and we can use a noise spectroscopy to gain information. What we do is, first of all, we use very high quality cameras. These cameras are single photon, each pixel has single photon efficiency. And we could treat each pixel as an individual detector. So we take an image of these atoms many times. So say we prepare the same sort of conditions and take 100 images. For every point on the camera, we can determine whether we have atomic shot noise or photon shot noise. And when we have atomic shot noise, we could correlate the different pixels together. And here's an example of some interesting things that we could do. So we're able to load atoms inside of a lattice, and we create two geometries. One where every lattice site is loaded with atoms, the other where every other lattice site is loaded with atoms. In principle, if you take an image, you can't tell the difference between them. However, if you do G2 spectroscopy, what you get is these things that you see on the bottom left. You see G2 correlation peaks with the separation. This separation of peaks exactly gives you the spacing of the lattices inside here. So it's a very powerful sort of tool. In principle, we could do this for G3 and G4. We propose a G4 sort of tool inside this paper. At the same time, we could actually have single atom detection. So this is from our lab in Bordeaux, France. We're using high finesse cavity and monitoring the light leaking out of the cavity. We've arrived at single atom detection at about 98% detection efficiency. What you see on the right is, on the left, we pass atoms. We just create our BC above the cavity, and we leak the atoms. As a single atom passes, we can see a detection event, which allows us to get single atom detection efficiency in one direction. We can also use these cavities for other things. So one of the things we want to do is we want to create squeeze states. Particularly, we want to create squeeze states in the momentum variable. Now, this is a very difficult topic. Usually when we create squeezing or entanglement, what we do is we create in a spin variable and then sort of using electromagnetic fields, transform that to a position or momentum state. This is not ideal because what you're basically doing is creating an auxiliary variable and using that to create what you want. But anything which can decohere the auxiliary variable can decohere what you're trying to create. It's better to create it in the variable you actually want. So using these high finesse cavities, we could do just this. We created a very large cavity. When the cavity is really long, the line width of the atom-light interactions become very small. It becomes so small that now you're sensitive to Doppler shifts, the momentum distribution. So therefore, you have a cavity which is sensitive to the momentum distribution, and you could use this cavity to create correlations between different momentum states. Here's the experiment we have, and these are the results I just want to show you. These are new results, by the way. What you see on the bottom is you see images of the BEC, and you see on the bottom right is the BEC. Then we increase the interaction with this very large cavity. This cavity can actually transport atoms to other spin states. Every blob you see is one photon recoil away. And our idea is to use a cavity to create correlations between them, and hopefully in the future create momentum squeezing for the atoms in the cavity. So just to conclude, although I know that there are many sort of platforms, I know in Vienna, you have these amazing platforms with the microresonators and molecules. I just want to point out that cold atoms have many advantages. They're isolated, tunable, easily accessible. we can create ground state for all variables, both center of mass and internal coordinates, which is not always the case, especially for the molecular people. Our protocols are deterministic and repeatable. We have single atom detection, and we can work directly in the position of matter space. All right, thank you.
Thank you very much, Devang. This was very interesting. I must apologize because I realized I should have invited all the experimentalists at DICOKI. They're not in their mailing list. So now you have to come to Vienna and repeat this. Marcus, unfortunately, is traveling today. He was aware of the talk, but he's on the way from the States to Vienna. Yeah, let me go for questions, first of all. Are there any questions? Please raise a hand or unmute. There is one by Eugenia.
Yeah, I just wanted to bring up, it's a really naive question. Certainly you have sources for non-Gaussianities of various origin. What do you use to identify the ones that are gravitational?
Okay. Well, okay, for my end, I deal more with getting rid of other sources. So for example, one of the things that we could do is we could look at, say you have decoherence channels. You could actually measure the decoherence between with 2-body and 3-body and see how they scale. And you can see their relationship. So for example, the Fetchbox resonance, you could reverse the sign. So any sort of decoherence that comes from electromagnetic fields would see a behavior when you reverse the sign of this decoherence itself. So for my philosophy, it would be this: to characterize how decoherence behaves with respect to the other 2- and 3-body collisions and temperature also, and then try to look for a decoherence that doesn't scale in that way.
Thank you. And I have a follow-up question, Marius, if it's okay.
Yeah, Eugenio, go. There is no other questions.
Sure. So I'm really fascinated by how large these condensates can get and how far you can get. It's really impressive. As a theorist, I always have this question that is, as theorists, we just treat it as an idealized condensate. And so when you tell me how many atoms or what's the mass, I treat all of it as a condensate. But I imagine that there's a typical scale over which you can consider it as a condensate that is not necessarily the full system. And so when we make these estimates, we use the full mass as if it was a condensate, but it might be that experimentally it's only fractions or portions of it are behaving as a condensate. So can you discuss that? Can you tell us what is the status?
So actually, sodium would be the only part BECs where if they give you a mass, you could say most of that is a condensate. So on rubidium, most of the experiments you see at the most is 50%. So when they give you the atom numbers, lots of times they can't really tell how many atoms are really in the condensate or not. They just give you the full atom number. Only about half is really in the condensate. When you go to hydrogen, it's 1%, 1 or 2%. But however, this is a really important thing because the more atoms you have in the BEC, the less it behaves like a BEC. So really, there's something about this this mix. So the more pure I create a BEC, the less of a common phase it has everywhere, is what I mean. So when I have this 50% or half the atoms in the BEC, I could really define a common phase. I could do interferometry, it's perfect, even though I have these thermal atoms. If I do with sodium, it tends to break up and create quasi-condensate phases, the more pure BEC I try to create.
Yeah, very good. That's exactly what I was wondering. So you get these domains or regions that you can consider as better condensates. So two questions there. One is, what do you use to check that a region behaves close to being an ideal condensate experimentally? And the other is for Richard, what is a good theoretical measure of this coherence?
Okay. So, I mean, the best thing is, which we could do in general, is interference. So actually, we have this optical trap as deformable. I don't have a picture of this, but we could take atom in a sort of a harmonic potential and split it into two. And we can control the amount in the other. So lots of times, if we're uncertain, we split it where we have 10% in the other one and 90% in this one. We do the experiment and then we interfere them. And that interference, we look at the interference fringes, and if the fringes are not perfectly straight, if there's sort of breaks in them, then we have an idea that there was sort of discontinuities in phase. Yeah. Now, if you don't have that, then it becomes a bit more interesting. Now, what you could do in this case, if there's big discontinuity in phase, is you could release the atoms from the trap and let them interfere with themselves. If there's a continuous phase, there's no interference with themselves. If there's a huge discontinuity, you could actually see kind of a turbulence or dynamics that occur, which is actually a different portion of condensate interfering with themselves. This can be done if you have really strong sort of phase jumps inside there. Now, actually, this is actually a point of research for us also, because when we reduce dimensions, we enter this regime where we have this phase breaking up. And the process in which a common phase at 3 dimensions goes to 2 dimensions, and you don't have a common phase, you don't have communication, for us is really fascinating because we don't know how this actually, how this works out and what's the physics behind it. Maybe if you could, if you could help us with that.
I'd be delighted to discuss more.
However, I would say that, so for example, in 1 dimension, there's no phase. So that you can't really define a common phase at all. There's no BEC. However, you're still in the ground state of the system. It's just that there's no discontinuity. You know, when you're cooling down, you don't have a discontinuous jump to this, to all the atoms being in a state. You have a continuous. So for this kind of physics, I don't know, to be honest, what's important, because we have all atoms inside the ground state. However, we don't have a common phase. We don't have this phase transition to this phase. I don't know if this matters at all for a lot of these things or not. Maybe you could tell us, because if we can live without it, the 1-dimensional systems would be fantastic. There's no 2 or 3 body interactions at all. Thank you. So if you want to discuss afterwards, let me know. There's Ikim.
Yeah. Actually, at the same.
There is follow-ups, Eugenio and Devang.
Yeah.
Yes. Akil.
Yeah. I actually had the same question again because I'm not. I didn't really get. So, do you have an estimation for how much, what is the, like, how large is the effect that you're trying to measure compared to all the other sources of uncertainty that's coming from all these effects that you discussed? Like, what I'm wondering is that how much improvements there should be. Can you really make this, I mean, not you personally, but can one really make these effects completely disappear, or what is the baseline for these, for instance?
Well, before I say something, Richard, I don't know if you have a more solid idea on this before I.
Yeah, I mean, maybe we would probably say the same thing. I don't know. I mean, in terms of, yeah, the main thing the biggest ever effect would be these interactions between the atoms, and as Devang was saying, it's the S wave which should be the strongest. These are 2-body S wave interactions, and yeah, we have a few ideas for how to look at how to distinguish gravity from these ones. The simplest one would be obviously to just suppress them enough such that you don't see them compared to the gravitational ones. Now that means, as Devang was saying, in principle, you can get to 0 interactions in these S wave using these Fetchbox resonances. Now, to get something, the challenge there would be what you're doing in that case is you're using an external magnetic field, and you know the value you want to get to make these interactions 0, but there will obviously always be noise fluctuations in the magnetic field. So you really want to get these massively under control. And right now in the lab, you couldn't get these under control enough to be able to distinguish gravity in this way. So this is something you need to improve on. I can't remember the top of my head, but it's, a few orders of magnitude. I think those magnets probably exist in the world. That there are magnets to have such low noise fluctuations, but they're not in BEC labs right now. But there are, Devang and I were discussing during the project, and there are other ways perhaps you could look at seeing gravity beyond these electromagnetic interactions, rather than just suppressing them enough that you don't see them. You could suppress them, but also fluctuate them. So, and these Fetchbox resonances are quite incredible. You can change the interaction from being positive to being attractive to repulsive. And of course, you can't do this with gravity. So by almost fluctuating these electromagnetic interactions, you can imagine you can distinguish these out from the gravitational ones. So that's another possibility. But all of these things, this is experimental challenges. Like, I don't think it's impossible, but it's like with it's equivalent to these other tests with entanglement. That's, of course, we're not there yet. It still takes a bit of time. But maybe Devang, you could say a bit more because you'll know more of the challenges than I do.
Well, actually, so it's interesting what Richard said about there are magnetic fields that actually have close to zero noise. That'd be perfect for this. They're permanent magnets, magnetic fields. And to give you an interesting thing about this, when the Nobel Prize for the BEC was first awarded, there's a bit of controversy because most likely the person who created the first BEC was actually a different person at Rice University. The problem was he was using these really good quality magnetic fields made out of permanent magnets, and he couldn't turn the magnets off. So he couldn't tell if he had a BEC for a long, long time. So one of the big problems is we have to use dirtier things to be able to image the BECs. One thing that, for example, in this paper in general, we try to do is we try to create a variable to which the other decoherence channels won't have much of an effect on. This is, and higher order correlations is kind of our way of doing that. So for example, one thing, losses that come about via three-body collisions tend to give which way information. So if we could create a variable that's symmetric in some sense, that doesn't give out which way information, we could kind of separate where the decoherence channels come from. But a big issue for us is two-body collisions with respect to gravitational. I personally don't, now two-body would be a huge thing. In fact, it'll overpower it. However, in principle, because two-body collisions, we could change the sign of that two-body interactions. Any decoherence channels that we see, we could test how it behaves on different sides of this process. And we could also go to a point where in one dimension, we could really tune it out to zero. So we could see how this behaves. Now, in terms of actual numbers, I don't really have any sort of numbers. I do know that we could reduce decoherence from two-body collisions by 5 orders of magnitude, experimentally speaking. Now, is the question, is that enough? I don't know.
With respect to what? Reducing?
So if you take a rubidium BEC itself, and okay, so take, for example, what we usually do. Say we take a rubidium BEC and we're just doing an interference experiment. Now we're looking at how this experiment decays with respect to two-body interactions and collisions. With respect to this, we could reduce that by about 5 orders of magnitude using the Fetchbox resonances. Three-body collisions, we could reduce 4 orders of magnitude. So what we're really just reducing is reducing.
You mean you can do this now in the lab, or this is something imaginable for the?
Oh yeah, well this is work maybe 4 or 5 years ago. I don't know what they do now. So I know 4 or 5 years ago we could do this. Yes. Now, but as Richard said, the limit we had was actually the magnetic fields we were using. We were sending current through there, and the current had noise, and this noise was limiting us. So if you know really well exactly where you want to be, you could design a permanent magnet setup, which can really be there. For something like potassium, that's really, that's possible. In which case you could get even better, these reductions themselves.
If you know where you want to be, what do you mean?
In terms of, so for example, if you know that you want to work with a certain atom, potassium, and you know you want to have 0 two-body interactions, we know exactly what magnetic field you need. You can use permanent magnets. Now, the permanent magnets, you can't really change the magnetic field so well. So if you know that that's the experiment you want to run, we could design a really nice experimental setup with very little magnetic field noise using permanent magnets. However, I mean, you know, when we're building experiment, we have students that need to graduate with theses. So if they're not getting results, then there's still a lot of physics we could do, but we have to change the magnetic field to do those physics. So in general, we don't design it like that. We design dirtier systems simply because we'll get results.
I see. Let's assume that one day this can be done. Do you expect it to be a tabletop experiment or to be some big facility?
Well, wait, let me see if I could go. So I could tell you, okay, right now, these are the type of experiments. It's a tabletop in a sense, but it's a tabletop because we buy a really large table that's really expensive. So it's not tabletop in the sense anyone considers it to be. This experiment took an entire room, or 2 rooms, because another room, we had to separate all noise. And this is very important for any type of experiment we're talking about. What we did here is within the walls, we tore out all AC lines. Because AC lines, even if there's no electronic equipment, the background AC lines really swamp our system. So we tore out all AC lines, we moved all electronics to another room, which is Faraday caged, and only brought DC inside here. So in this sense, yes, we could do it in a tabletop. Now we're actually, for example, most of the stuff we could get rid of with the newer generation of vacuum systems, with titanium vacuum systems and things like this. However, if you want the really large atom numbers, if you want to really get to 10 to the 9, 10 to the 10 of sodium, you're going to need these huge ovens and these huge Zeeman slowers. So that first half on the left-hand side, for foreseeable future, you're not going to get rid of. So yeah, it'll be tabletop, but it will be a very special table.
Still, but it fits in a room.
Yeah, it fits in a room. It fits in a room, yeah.
So is the noise a concern only, from the source that is generating the magnetic field, or also the environmental noise? I mean,
yeah, both. So if I could show you this
like
sort of thing.
Cell phones or even the magnetic field of the Earth to you.
So if you look at this sort of thing, we're able to identify Fetchbox resistance where the window we had to do our experiments, for example, these experiments here, was 1 milligauss. Now we had to be at 1000 Gauss, and at 1000 Gauss, we have to be precise to 1 milligauss.
You have this precision. So
we were only only because of electronics. So for example, all of the power supplies, everything has switching noise, which is in the hundreds of kilohertz. This destroys you. The AC lines destroy you. So yes, we're swamped in noise. The one that doesn't matter is Earth's magnetic field because it's a constant DC. So we could always offset that. But all the AC stuff is a destruction. In fact, most people don't have large BCs like us because they're limited by noise in their magnetic traps. This is something we discovered, and it took a year or 2 just to design electronically a good enough magnetic field system to create that 100 million atom condensate.
I see.
One thing I'd add to that is that most noise tends to be Gaussian, and the advantage of this is because we're looking at non-Gaussian, that doesn't show up. So you can sort of don't have to worry about Gaussian noise. You only have to worry about non-Gaussian noise. But
is that the case also? Okay, I know I'm on this paper, but I've always been uncertain about this. So the two-body collision itself, the collision effect, is that a Gaussian? Because it's electromagnetic in nature.
No, it's non-Gaussian.
Okay.
That's effect. Yeah, which is why it's a problem.
So I was asking because I'm not an experimentalist, so I may say something stupid here. But do you know that in Vienna there is the second most silent site in the world in terms of electromagnetic noise? The first one is in Antarctica. The second is here it's a tunnel in a mountain.
Yeah.
And that's where Marcus is doing the gravity measurements.
Mm-hmm.
They built the whole tunnel in some sort of rock that has no magnetism, and they used only plastic. There's nothing metallic in there, exactly for that. For the experiments of Marcus, because it's even more also acoustic noise for his experiments are really a big issue. So this is the case.
In these particular experiments, one thing is, so when we have noise, we always have noise, but it's what frequency the noises occur at. With atomic systems, because they're deformable, because I could change the trap parameters, I can make all the interesting interactions occur in a frequency regime where I don't see noise, or as much as possible. So for example, in a building, in the buildings we have here, we have noise in 100 hertz, 50 to 100 hertz, acoustic noise. So I could design an experiment where all the interesting things, all the dynamics occur at 1 kilohertz and reduce that amount of noise. Or for example, for our detectors to detect brain waves, brain neural pathways, there's magnetic field noise everywhere. However, if I go to megahertz, I gain 9 orders of magnitude in terms of noise. So we try to do the entire experiment in that megahertz regime, because it's almost impossible to fight noise unless you do what Marcus does. So now he doesn't have the capability to shift his experiment around to work in a noise-free regime. With ultra-cold atoms, you do have this capability, kind of.
You do not, you said?
You do have this capability. You could kind of, by squeezing the trap, you could increase the dynamics inside the BEC itself. So any sort of, so for example, any sort of, if you have a phonon and the phonon's propagating, if the trap is very weak, it propagates at a lower frequency. So all the noise would matter. But now if you just squeeze that trap, now all the dynamics occur at a different frequency, and you can kind of separate the frequency of the noise with the experiment, which is a huge advantage.
I see. Thank you very much. Is there anybody else that wants to comment? No. I would suggest we stop the seminar now. Just stay for a second, though. I will stop YouTube. Thank you very much, Devang and Richard, for the very nice talk.